So welcome to this week's nuclear engineering seminar. Thanks again, everyone, for being here virtually, and as always, looking forward to getting to do this in person again in the near future. But in the meantime, we still have some amazing speakers who are going to give us some amazing presentations throughout the semester, and this is definitely one of them. I want to introduce you to this week's speaker. It's Bill Glass, who is a technical advisor with more than 40 years experience working on non-destructive evaluation, materials characterization, and robotics for inspection in hazardous environments, both in the United States and Europe. Bill is a Wolfpack alumni and has both a bachelor's degree and a master's degree from NC State, the bachelor's degree being in mechanical engineering and the master's degree being in biomedical engineering. His work at Pacific Northwest National Labs supports the Department of Energy, Nuclear Regulatory Commission, and Department of Homeland Security projects in the area of energy, advanced reactors, nuclear storage, test and evaluation. Recent projects that he's worked on include high temperature sensors for heat exchangers, guided wave ultrasound sensors, and cable inspection technologies. He also supports strategy development for national security leadership teams and participates in and manages several large projects there. Before joining Pacific Northwest National Labs, he served as Chief Technical Advisor for Areva and Framatome, providing technical and project management oversight on inspection, design, and condition monitoring services for nuclear power plants and research reactors in the nuclear energy market. He advised company leadership and technical teams on design, engineering, maintenance, installation, and repair of nuclear steam supply components and fuel for nuclear power plants and reactor services worldwide. He has also overseen large proposal bid review, non-destructive evaluation, intellectual property, and competitive intelligence for Areva and Framatome global NDE solutions. And our speaker today brings gifts for our students, which is hard to do in a virtual environment. But if you all take a look at your chat, you will find a URL posting for a job opportunity at Pacific Northwest National Labs. This job is based in Richland. And so with that, and thank you for the, on behalf of the students, thank you for the job posting, and I will like to hand it over to our speaker for this week.
Great, thanks, Steve. Regarding the job posting, pay attention to that quickly. I don't know when it will be closing, but soon. So if you have interest and you fit the criteria, we'd love to talk to you. So today, though, I'm supposed to talk to you about NDE techniques for monitoring advanced sensors. Kind of before I get started with that, though, I want to give a little plug for PNNL. PNNL is part of the DOE's system of national laboratories that originally grew out of the Manhattan Project, focused on building the first A-bombs. That pack of folks included Los Alamos and Oak Ridge, Hanford, which later sort of mutated into PNNL, and other labs across the country. You can see that there are now a system of about 17 labs in the DOE Science and Technology Complex. Why doesn't it advance? Frozen.
Yeah. Technical difficulties?
Yeah, let's see what happened. Here we go.
There you
go. Okay, so we use the page down button and that seems to work. So like I said, PNNL is a national lab. We've got most people on site. There are over 5,000 people, though, associated with Pacific Northwest National Lab. Here you see an overview of the main campus, but like I say, there are people in Seattle and Squibb and various locations, including myself, who I'm currently just recently took a deal where I'm working mostly away from campus, and I've moved back to North Carolina, but still working for Pacific Northwest National Labs. We've got focus in the areas of energy and infrastructure, energy security and emergency responses, energy efficiency and renewable energy sorts of things, nuclear energy and regulatory work. That's the area in which I work. Also, we've got division that works on carbon management and fossil energy and environmental management. So there are lots of different groups, but it offers some interesting opportunities for work. This is a plug for our belief in diversity, which is critical and vital to our organization. Our employee resource group offers professional, educational, continuing education opportunities. In general, education and personal advancement is encouraged. The lab is really a somewhat academic and collegial type of environment where we have host speakers on a variety of subjects, some technical, some not so technical, particularly associated with most recently All Lives Matter and diversity sorts of issues. So that's the plug that I wanted to share, except for the note that we do have positions open, including the one that I just posted on the chat box. But mostly what I wanted to talk to you about today is advanced reactors and NDE things associated with that. The general presentation outline will address sort of why advanced reactors. It will address some of the various designs and history and gaps associated with advanced reactors, and then P&L initiatives to try to plug some of these gaps. These include high temperature ultrasound sensors for structural integrity and flow and temperature, magnetostrictive cold spray for high temperature sensors, online heat exchanger tube monitoring, acoustic power and modem for virtual penetrations, fiber optics for motion, temperature, and material identification, and some of the peripheral semi-technical stuff associated with advanced reactor websites and databases and ASME code considerations. Whoop, hang on here. We've got to do something. So this came from something where I had to narrate and make a video out of it, and obviously that still goes with it, and I didn't realize that until just now, but I will tell you about it, me myself personally. It's the money. That's why advanced reactors, like I say, I do like this chart. If you look at can everybody see my cursor so that I can point?
Yes, we can see it just fine.
Great, great. So this is the reference LWRS conventional reactor. This is mature technology, and it's unlikely to change much. This represents the new designs that are being developed in in Georgia with the AP1000 and all of the other LWR technologies. That's marginally competitive with natural gas, but virtually all of these other advanced reactors, when surveyed, project a significant cost savings over the traditional nuclear power reactor, some of them significantly. Plus, these advanced reactors, they also enjoy the benefit of, in some cases, being waste burners, where the amount of waste is really a fraction of what the conventional light water reactors produce, and or will be able to burn up some of the fuel from the traditional fleet. Yeah. Whoop. It's not paying attention to my cursor. Okay. First generation molten salt reactors plan to rely on known component technology. Let's see here. Okay, so they require pressurization of the fuel system to avoid pump cavitation, coupled with spray rings to evolve fission gas and tritium exchangers. In general, though, the kinds of things that are associated with first generation MSRs are that it's important to consider all of these kinds of things in the design of these reactors. Although our experience base is not very wide for molten salt reactors, there is experience for advanced reactors, particularly the sodium reactors. The experience related to sodium reactors is based on a number of plants that have been operated over the years in particularly in France and in China, Russia, and India. So there are literally numerous decades of experience with these sodium reactors. And a report was compiled looking at where failures occurred in these molten salt, in these sodium reactors. And by far the biggest component of these failures was associated with the heat exchangers, followed by fuel cladding failures, pipe and vessel failures, and pump seals and internal kinds of things. But this is kind of the distribution that would probably be expected in the advanced reactor, the full set of advanced reactor series, including the molten salt reactors. So now I'm going to go over a number of different designs of advanced reactors, just to give you a feel for what these structures are. And they're all quite similar. So we'll start with the liquid sodium reactor. Here you've got a vessel that you see where it's kind of a pool of molten sodium, and inside this vessel here there is an inner vessel where you pump fluid from the hot portion of the vessel, that is the output side here, and it then goes through a first heat exchanger and then back into the cold lower leg. And inside this inner vessel are reactor core fuel components. The fuel here heats up this fluid so that you get heat that goes into this heat exchanger. Now in the in this design, there are two sets of heat exchangers. There's the low pressure heat exchanger shown here, and here this pumps the fluid is then pumped into a secondary heat exchanger where you heat up the water-steam mixture, which then ultimately goes to drive the turbine, which drives the generator, which makes the power. In this particular case, operating temperatures were like 360 to 600 C for all of these kinds of sodium fast reactors. And there, like I said, there was serious operating history for this particular type of design. Now we'll go on to, let's see here. Now we'll go on to a very interesting design being promoted by Hydramine. Hydramine is a lead reactor with a single stage spiral heat exchanger. This produces a very compact configuration, and we are actually working with Hydramine on this particular heat exchanger to try to instrument it and see what the condition of these tubes are, and I'll talk about that a bit later. But one important thing to note about all of these designs is that it's tough to get access to them in order to do inspection kinds of things. They are radiologically very, very hot. Also, they are thermally very, very hot. And it's undesirable to shut these plants down in order to be able to go in and do anything to them after they are started. They have to be designed for remotely decoupling most of these major components in order to be able to continue to operate if you need to replace anything or to inspect anything. This is why it's very, very important for online monitoring to be incorporated into the system designs. The online monitoring, I believe, will be virtually essential for the NRC justifying these things under continued operation. And candidly, this is a huge gap that we are trying to help fill at PNNL. Online monitoring, currently we don't know how to do that at the temperatures and in the configurations that these reactors are at. This is one of our efforts, though, to try to make this a manageable thing for this Hydramine design. Next, we'll look at the Keros Power TRISO power system. The TRISO designs, here you see the 0.5 to 0.7 millimeter small ball, which has the fuel kernel in it, and it's shrouded by several layers of protective material to keep the fuel encapsulated. And then several thousands of these small 0.5 to 0.7 millimeter diameter balls are then housed and encapsulated in these tennis ball size pebbles that can be actively loaded and refueled into the reactor real time, such that as it goes into the reactor, these balls get circulated, they produce heat, but as the balls pass through, they can be online inserted and retrieved. This is a design that's similar between both Keros Power. Well, this particular design is primarily like the Keros Power arrangement. Once again, though, you've got one or two levels, in this particular case, 2 levels of heat exchangers before you get to the turbines and the generator to produce the power. Again, though, these are tough to inspect. You really need to have online monitoring kinds of things. Dissolved fuel MSRs, this produces even a more complex inspection issue, because this is radiologically, this is the hottest kind of coolant fuel, in that the fuel is dissolved in the molten salt. But at the same time that you get more difficulty for inspection and a hotter environment, you also get the benefit of having the fuel in intimate contact and dissolved in the coolant, so that it's probably the most efficient way to produce the heat. There's less thermal losses due to the salt having the fuel directly in it. Again, there are heat exchangers in this system. In this particular case, though, and the idea for the FLIBE system is that their last stage, where they have pressure, is a gas heat exchanger rather than a salt or water heat exchanger. So that's a little bit of an aberration for that kind of design. Overview of some of the main distinct types of systems. We've got the molten salt single fluid. We've got the molten salt fast reactors. All of these are compared to LWRSs like the AP1000. Then there's the sodium prism design and the TerraPower IMSR design here. All of these things, though, if you look at the hot leg temperature, the AP1000 has the lowest hot leg temperature, and this is where we know the most about components operating. All of these other designs go from 5 to 700 C, which is really hot. And the material gap for these kinds of things is significant. We are trying to help plug some of that gap, but right now and today, I'm going to talk mostly, though, about the inspection gap. PNNL initiatives for particularly the inspection gap includes these kinds of things: high temperature cold spray magnetostrictive EMATs, acoustic emission sorts of things, high temperature piezoelectrics for online heat exchanger monitoring, modal optical sensors, modal saw wave sensors, molten salt chemistry, monitoring and corrosion monitoring using fiber optics, advanced reactor systems, web database, and code activities. So this is a little bit of a physics kind of lesson. Magnetostrictive electromagnetic EMATs are known to produce a strong acoustic or ultrasound pulse by pulsing the magnetic field in the coil that is under the mag bias of the magnet. And this is a Lorentz force kind of thing, and the reciprocal Villari effect allows you to sense using the same basic principles. One problem with magnetostrictive material, though, is that it's normally adhesively applied, and this doesn't really work well with nuclear applications. So PNNL has been exploring use of magnetostrictive material, and instead of using adhesive applied ferrous cobalt strips, we've been looking at nickel and other magnetostrictive material to use and metallurgically bond these materials to the substrate, and thereby generate guided ultrasonic waves with a suitable material that can live for decades attached to a nuclear power reactor. We demonstrated that we could use cold spray, and we are in general a fan of cold spray because it offers a number of high potential mitigation and repair technologies, as well as serving as this magnetostrictive material. The cold spray happens by accelerating 10 to 100 micron particles up to about Mach 2 or Mach 3, where they then impact on the material substrate. They don't get really near the heated, the melting temperature of these particles, though. Rather, they form a splat, which is a metallurgically bonded particle to the substrate. You can build up significant layers with this cold spray material. Here is a real picture of a cold spray system like what we have at PNNL, and what you can get to either do factory cold spray work or in the field in situ cold spray work on these systems. So there are a number of possible materials that you can use for cold spray listed here. Some of them have higher Curie temperatures than others. This is an important consideration when choosing material. Most of the work that we did for initial qualification was with nickel, but here the demonstration was that with the on a cold sprayed plate, we can get a similar response, or in some cases even better, with the cold spray. The cold spray is on the right, and the ferrous cobalt adhesive based strip is here on the left. And from an ultrasonic perspective, I like the one on the right as well, or better than the one on the left. So that generally demonstrates that this is a viable thing. This shows the relative amplitudes of things, showing that that it does make a difference how you do the cold spray, and there were a number of different recipes that we used, but the bottom line was that when we compared the cold spray versus the adhesive patch, we get similar kinds of responses. So we were pleased with that. And this is a technology that is licensed to a company, actually a company just north of us here in Virginia, called Interspec. So it's a real commercial thing now. One can use the magnetostrictive material to do lots of things, including structural health monitoring or flow monitoring. This is an application where we're trying to adapt a magnetostrictive material to see flow in a pipe, and that's done by looking at the differential time of flight from the transmitter to the receiver, and we send it both ways and look at it differentially, and that is proportional to the mean velocity of the material in the pipe. That's pretty important. Flow measurement in these advanced reactors is an important criteria that's darn hard to do at these kinds of temperatures. As I said, this is material that is licensed from PNNL to a commercial vendor, and so this is a real commercial thing. And one of the goals of the national labs is not only to develop science and develop technology, but to try to help facilitate the migration to an industrial application. This was my first licensing of this kind of technology from the national lab, and we were hugely pleased that we worked that out with them. So that was a happy story. Next, I'm going to talk about heat exchanger sorts of things. This is a typical power plant tube bundle, shell and tube heat exchanger configuration. The actual length of these tubes is typically sort of 20 to 30 meters. And we would have a fluid inside the tube and a fluid outside the tube, shown here in blue. And the idea is to transfer heat sometimes from the blue to the yellow, sometimes from the yellow to the blue. In this case, I've got the cool fluid shown as blue, so heat would be flowing from yellow to blue. These tubes, where'd my cursor go? here. So these tubes are joined to a tube sheet, which is sort of 1 to several inches thick here. They are welded so that the cold fluid is completely separated and isolated from the hot fluid. The desire is to only have heat transfer across these the significant surface area of the heat exchanger tubes. Now, in traditional plants, you have a tube end access plenum, and you can pass an eddy current probe or some other kinds of NDE inspection probes through these tubes, and we do a really good job of characterizing whether there are flaws and problems in these tubes. But in the advanced reactors, that's going to be very difficult to get a robot even in there in order to pass these sensors through the tubes. We need a way to monitor the condition of these tubes permanently and online. So it is possible, and many people, not many, but some people have demonstrated that you can produce and put a sensor here at the end of the tube, inside the tube, and send an ultrasonic wave up along this tube. And it travels quite efficiently, and you can see relatively small flaws down to 50% through wall small pits from a sensor mounted inside the tube. You can go into a heat exchanger and do that when the heat exchanger is offline. But if it's online, it's tough to do that. Online, when the heat exchanger is operating, this is a high flow area. You've got a great deal of difficulty trying to get the wire out of this plenum, plus it would occlude the fluid and render that tube way less efficient, which is undesirable from the overall operation of the plant. If, however, by contrast, you put the sensor on the outside of the tube, here, then it's in a relatively stagnant flow zone, and you can monitor the tube condition from the outside, or the tube OD. This is possible to do, but only if you do it in conjunction with the fabrication of this heat exchanger, because otherwise this area is just completely inaccessible. Our effort for the Hydromine project is to be able to mount sensors on the outside of these tubes and then bring the wires out into a multiplexing instrument such that we can do online monitoring of these heat exchanger tubes. We are making progress on this. I am extremely proud of this particular image. Although it's pretty small, it's not bad as you look at ultrasound kinds of things. This was an early indication of a 50% through-wall pit, which is shown physically here in the photograph. Here, a bit bigger is the 100% through-wall hole in the tube. We really want to catch these things before they get that big. Here is a 50% notch further down the tube. This is, in this particular case, it's only a 10-foot tube. We are having fabricated, though, a full 30-meter tube, and we expect to have similar kinds of performance with 30-meter tube. So we also wanted to hang on. So we also, excuse me, wanted to confirm that we could have a relatively small section of the tube that would be instrumented with the array of sensors. And so we did a test where we had the array here over a small portion of the tube, and then we moved a sensing element first axially, like 2 centimeters, and then 5 centimeters, and then 20 centimeters down the tube, and then moved it circumferentially all the way around the tube. And here you can see that at at, at 2 centimeters, we are we still have some change in the sound level, but as we go to 20 centimeters, the sound level or the acoustic energy is relatively flat all the way around the tube. So a small array can fully cover the tube after it gets up to 20 centimeters away from the sensor elements. So that was pleasing. One of the studies that we have done in order to kind of qualify that kind of thing. So here we're back to the idea of how you will have a sensor. Here is the sensor at this end of the tube. The sensor will send a guided wave into the coiled tube, round and round and round. And ultimately, if there is any flaw or crack or pit or anomaly in the tube, some of that sound will reflect back to the sensor element here, and we think that we can make these sensors last in this particular case simply in the argon environment, where the sensor is mounted on the inlet riser, and the location of the sensor would be here, and we can send the signal all the way around the tube. So that's a current project that we're looking at. How are we doing on time? Yeah.
You're doing okay. You got about 20 minutes, 25 minutes left, including time for questions.
Okay. Well, so I'm going to talk about this now, which is a little bit of a lower TRL level thing. TRL goes from 1 to 9, and 9 being, you buy it, it's off the shelf, you just buy it and use it, everything's done. 1 is it's just a twinkle in somebody's eye for an idea. This is like at TRL level 3 or 4, where we've got a commercial microprocessor electronics set that is coupled with another electronic set on the outside. So we've got an electronic set on the inside of a reactor vessel, theoretically, and electronics on the outside of the reactor vessel, theoretically. And then this electronic set is connected to an ultrasonic piezoelectric sensor shown here. And then we are transmitting sound through about a foot-thick steel plate to a receiving ultrasound sensor here. We can also transmit encoded information via an acoustic modem that not only harvests the power, but also deals with signal interpretation. And so the demonstration here is that we can type something or have a signal on the inside of the reactor vessel, and it goes to its encoded information via ultrasound to the ultrasound transceiver here, and it's received on the outside with this ultrasound transceiver. And also we can transmit power, so that inside you get both power and communication. Now, right now this system works up to 100 C. We think we know how to make it operate readily up to 200 C. We're working with others to make it operate to 350 and beyond, which is where we really have to get in order to be able to do this kind of thing commercially and turn it into a real product. But this shows, I think, pretty cool technology that's looking forward to the future, and this will be really important for the cost efficiency of these plants. If we can minimize the penetrations and get signals in and out of the reactor. I think this is cool technology, and more to come on this as we get with some of the people who are working to make gallium arsenide electronics and other types of electronics that are needed to operate at these higher and higher temperatures. But that's going to happen soon, and when it does, we'll be ready. Meanwhile, we've got folks who are interested in this kind of technology for the lower temperature applications. You'd be surprised how many people want to do stuff without punching holes in stuff. Fiber optics. Now we're changing modes to various fiber optic sensors looking for stuff in the advanced reactor environment. This sketch shows options for introducing light into the environment, optical and fiber optics for applications where light goes through the coolant is possible for salts where coolant is translucent or transparent. It's harder for liquid metal things like sodium and lead where the material is not transparent. But even there, though, there are fiber optic sensors where the light stays in the fiber and you can get the kinds of information that you would like to have, which include things like temperature. You can still get motion in the fiber if you have it anchored to structural elements. But the point is that, you know, we can either get fiber into the reactor and into the coolant through penetrations, or we can have sort of periscope types of things where we get into the coolant. In many cases, you want to also include lasers in these kinds of systems. But there are all kinds of things that you can do with fibers and lasers, and they do work in these kinds of molten salt and liquid metal environments. One particular technology that we have acquired most recently is the laser vibrometer, where we use the laser to measure motion of structural components in the system, and that's kind of cool. We've had several projects within our little NDE group to use this laser vibrometer, and it's a heck of a tool. It's not cheap, but it's a heck of a tool, and these kinds of things will get more and more cost effective, and they can help with these advanced reactors. We are pretty convinced. Chemical characterization of salt is a real important thing. You can do that with lasers through fiber. In this particular case, we've used the fiber and laser to look at a number of different peaks in the FTIR to try and characterize various components in the salt. And as you're looking for particularly corrosion types of behavior in this salt, it's really important to detect when things start to degrade, when you start to get contaminants in the salt. This laser spectroscopy is really instrumental in finding these kinds of things. Now, as the NDE guy, I keep pointing out to folks that it's good to know when you have corrosion going on and about how much it is based on the laser thing, but it's absolutely important not only to know that you've got it going on, but you need to use traditional kinds of techniques like ultrasound and other sorts of NDE techniques to find where it is so that you can know where to go in and repair and fix. There are lots of different sensors that are going on right now, and PNNL has helped INL. We've collaborated to put together a nuclear energy sensor database, and we are populating that continually populating that. You can get access to it. The link is shown here at the bottom of the slide. These slides will be available, but this has a number of sensors, and it also describes sensor needs to try to align the sensor vendor communication with perceptions for needs. This is a tough thing because there's not a huge call for these kinds of things, since these advanced reactors won't be built for another 10 years probably. And then in 10 years, the number of these sensors might not be huge, but the national labs, various universities, various entities are building these kinds of sensors that either do work in these kinds of environments or theoretically can be made to work in these kinds of environments. And it's important to give designers of these reactors hope that they can have sensors that will do what needs to be done, and give sensor vendors feels for what the environment is that they need to design these sensors for, and you know, try to bridge the gap. This is, I think this is a good initiative, and we'll see how well it's actually used. It's tough to get people to look at what's available, but if you make it easy, lots of times they do. PNNL has also been active working in code space. The ASME Section 11, Division 2 was, after about a 15-year development effort, was finally released, published July 1st, 2019. It does address not only light water reactors and traditional reactor environments, but it also has words in there about how you would go to qualify systems for advanced reactors. That doesn't say it has all the answers, but it does provide guidance for how that can be done. And the watchword for all of this code activity now is reliability and integrity management, or RIM activity. And there the focus is on demonstrating, proving that you have a reliable barrier of the highly contaminated hazardous material. You keep that away from the general public. That's what the NRC wants to do. That's what the NRC mandates that these reactor designers do. And one of the only really practical ways to do that will be through online sensors and monitoring kinds of things. I am convinced that that's going to be instrumental to the licensing of these plants. So in conclusion, advanced reactor technology promises lower cost, safe, and sustainable energy. There are serious technology gaps, though, that must be bridged before we can really realize these kind of goals. PNNL and DOE have several initiatives to help bridge these gaps, and I've mentioned some of them, including high temperature ultrasounds for structural integrity, flow, and temperature measurements, magnetostrictive cold spray for high temperature sensors, online heat exchanger tube monitoring, acoustic power and modem for virtual penetrations, fiber and optic guides for motion, temperature, and material identification, and the advanced reactor website and the ASME code stuff. So that was kind of the pitch and the introduction. I am now completely available for thoughts, questions, comments.
All right.
What do we got?
Thank you very much for an awesome presentation. I would encourage the audience, if you have a question, either raise your hand in the participant window for Zoom, or if you prefer, you can post your question on the chat and I can read the question as I moderate. So at this time, does anyone have any questions? Alex.
Hi there. Thanks for the great talk. So for the launching the acoustic waves, has there been serious consideration for using a photoacoustic method as opposed to using the magnetorestrictive effect, meaning focus a laser into a target and try to ping it that way?
Well, so the answer is that all means are considered. Um, there are you can use photoacoustic laser sorts of things to generate pulses and to sense pulses, um, and that's known. The idea of uh, getting a pulse into a molten salt environment is possible because the molten salts are translucent or transparent. That's way harder in a lead or sodium environment because they are opaque and light doesn't travel through those as well. We use um, we use those kinds of techniques uh, where we can and where it's appropriate. Candidly, the photoacoustic pulse generated thing is it's an ugly pulse. If you're a UT guy, you would vastly prefer a cleaner either EMAT or piezoelectrically generated pulse because it's specific. You can get a specific frequency and uh, desirable characteristics out of that better than you can with the photoacoustic thing. Uh, but in some cases where you want to truly be non-contact, well, man, that's the way to go.
Mhm.
So yes, we have used that. Um, uh, we've used that in an application that I can't really talk about, but I'll tell you that it was there was a crucible involved and there was a window, and we were looking at a forging kind of situation through a window where we generated the pulse and sensed the ultrasound and got lots of interesting information. So it's a cool technology.
Well, that would bring me to a follow-up question, if I may steal that
Sure.
just a moment of your time. You were talking about the quality of the acoustic wave that was propagating that you can get from a piezoelectric, say, versus a photoacoustic. Uh, um, the sound waves that you showed, well, I mean, there are a lot of squiggles and oscillations, but it's the question I would have is how do you quantify that kind of squiggles and I mean, do you try to do some kind of Fourier transformation on it and look at some kind of scattering? I mean, like how do you quantitate those signals in the first place? I mean, or is it mostly just time of flight at this point?
Um, Time of flight, if you know the speed of sound in the material that you are interrogating, time of flight is really helpful for locating where the reflection occurs. Um, there are, our world though is signal analysis where we do Fourier transforms, Fourier and inverse Fourier transforms, correlation analyses. I'm a big fan of correlation analysis, autocorrelation, and cross correlation kinds of things, where you take the signal and you then statistically map it against the received signal, and you see, what looks the most like the applied input. Uh, but through the magic of MATLAB and Python and other signal processing kinds of things, um, before the presentation, we were discussing the merits of uh, quick and dirty analysis using Excel. I'm a big fan of Excel where it has the horsepower to do it, but MATLAB has lots of neat canned routines, and we've got PhDs and postdocs who want to apply their own special wrinkle of signal processing kinds of things. So, you know, a lot of what the group does is takes a signal and then cleans it up through various approaches.
Thanks.
I'm not sure that answers the question, but
I mean, I
short
guess,
answer is that
I'm
a lot
wondering,
of stuff.
is the analysis at the point where I could take a screwdriver and scratch one piece of the tube, and you can say, hey, that was a scratch. And then I can go and take some sandpaper and rub down on another part of the tube, and you can say, hey, it's getting thin over there. That kind of, you know, is the quantitative analysis at that level yet, or is it still?
Well, so NDE, non-destructive evaluation, is a broad range of technologies. Ultrasound and radiography are can be applied such that you get very, very fine resolution of an image of the material that you are interrogating. Ultrasound can use robotic scanners such that you know, you get pixel interrogation sizes that are on the order of fractions of a millimeter. The same can be said for X-ray kinds of things. Electromagnetic stuff is more surface related, but still it can penetrate up to, in some cases, like a centimeter or more. You can develop very fine images of these kinds of materials. The challenge for these advanced reactors, though, is that we want to interrogate large volumes of material with stationary sensors that will interrogate those large volumes of material. So you trade off the spatial resolution and your ability to know exactly how deep and what kind of flaw you've got for a temporal kind of thing where you can do signal processing and you see that things are going on, but sometimes you don't know exactly what's going on. You have to then apply other techniques to go find out what really is happening and whether you've got to shut the plant down or, well, whether you've got to replace the component or not.
All right. Great, thank you.
So we got a couple questions on the chat. Let me work through these really quick. First question is, how many years do you expect that the advanced reactors to be utilized or to be on site and active according to your experience? How long is it going to take for these to start becoming a reality?
Well, so interesting question. To me, it's pretty obvious that the money should be there, but the investment is so huge that it really requires a government industry partnership to actually make it happen. And that's going to be sensitive to politics and the available money.
They just announced that, was it 160 million for, there's the two companies, one doing the sodium and one doing the high temperature gas reactor.
I was just gonna bring that up. The 160 million, that sounds good.
It's not.
But you'd be surprised at how
Yeah.
how quickly 160 million can go. These plants, order of magnitude, are well, the traditional light water reactor plants. I know Framatome Riva, they sold one of the first of these plants for about 2 billion to Finland. And they sold it to Finland and they said that they could build it in about 6 years. Well, 10 years later, it's still not started completely. They've undergone some hot functional testing, but it was more like 6 billion for the one plant rather than 2. Westinghouse is having similar painful budgeting experiences with their plants in Georgia. The Chinese, for various reasons, they have been less plagued by cost overruns, and they have managed to build some of these plants. But still, we're talking for a Gen 4 type plant, which is a high power plant, we're talking sort of $2 to $5 billion. A lot of money. Now, over the life of the plant, they're still huge money makers in that, based on the cost of power today, the capital cost will be paid back within 15 or 20 years, and then it's just going to be a money-making machine. But these plants are expensive. On the advanced reactor side, we don't really know how much it's going to cost because there are still these technology gaps. And I want the government, the DOE, to put more effort into plugging these gaps so that the industry can get on with building them and start producing cheaper power for you and me and everybody else. There are still, though, a lot of gaps, and I expect we are at least 10 years down the road before all of those are plugged. Now, that doesn't say that we're 10 years necessarily before some demonstration reactors are going to be built, but they will be under limited licensing, and shortly after some of these get built, we'll have to seriously go into retrofitting and plugging some of these gaps.
Thank you. We got one last question from another one of our attendees on the chat room.
Sure.
So this question asks, for an ultrasound technique, it is important to optimize the frequency to achieve maximum data transfer rates. As temperatures can affect the wave speed in a material, how important is it to take variable material temperatures into account in order to maintain optimal data transfer rates?
Well, that's a trick question. On the one hand, if you want optimal, then yes, you've got to consider temperature and frequency, bandwidth, and all that kind of stuff. Where we are right now with our acoustic modem and energy harvesting ultrasound, it works pretty well at room temperature, and from what we know of how much change temperature is going to have on frequency and transmission, we think that's going to be the least of our problems for the acoustic modem transmission, because it's not optimum, but it does work. One thing to learn about engineering is frequently you don't care about optimum, you just want it to work. And so right now we're pleased that it works, and for this particular application, we're relatively insensitive to temperature until the temperature fries the electronics, at which point it doesn't work.
Thank you very much. So with that, I know we've hit the 5 o'clock hour. I would like to thank our speaker for a wonderful presentation this week. I would like to remind everyone that next week's presenter is Dr. Nathan Su from the U.S. Nuclear Regulatory Commission, who will be talking about probabilistic risk analysis and risk-informed decision-making at the NRC, discussing some of the trends and challenges they see there. So again, thank you very much to our speaker, Bill Glass, today, and I look forward to seeing you all next week. Thank you very much.
Thank you all. It's been a pleasure.